Visteon Corporation. I'm sure the first question is, who is that? So we'll talk a little bit about that. We can skip the personal introduction. That's me. Different shirt, but that's me. Yeah, I've got quite a bit of experience in software architecture, software design. Solution architecture is a more recent focus of mine. I've worked in the auto industry almost the entire time, different aspects. Now I'm in the cockpit electronics area. Prior to that, in my very early days, I did some database work on some of the controllers in the manufacturing plants. Okay, so who is Visteon? At a macro level, Visteon is an automotive supplier. That's a vague description. A little more granularity, Visteon is an automotive electronics supplier. Slightly more granularity, Visteon is a cockpit electronics supplier. So what does that mean? I've listed here the domains of typical cockpit electronics. The instrument clusters, heads-up displays, infotainment systems, other displays in the vehicle, connectivity solutions, Bluetooth and whatnot, and into self-driving more recently. So I tend to focus more on the left side of this with what I do, but software architecture is software architecture. Okay, so since we're talking about kind of the world I live in within the company, instrument clusters, which you're looking at. And that, many of you may recognize that from today, but I can tell you just a few short years ago, they did not look like that. And when I started in 1990, they definitely didn't look like this. So that's kind of what we're going to talk about today. Can the same architecture that worked in 1990-ish work on something like this? So what's unique about this? Well, this is called a digital cluster. Why is that? All right, well, because initially we called clusters analog. Why is that? The same as your watch. It had dials. It had a rotary odometer. It had a mechanical pointer for telling you what gear you were in. You won't see any of that there. That is one large display with a big graphics engine controlling those same elements I just spoke of. So this is a digital cluster. And where are we going? If you recall a few slides ago, I showed the domains, instrument cluster, heads-up display, and so on. The trend is to centralize many of those domains into one controller, which will be called an integrated cockpit controller. So you'll have the cluster functionality and the infotainment functionality and the audio functionality in one centralized controller that has many cores on it, many different operating systems, hypervisors, and all the like. And so on the right-hand side is why would a supplier be interested in a solution like that? And market research shows that's where the industry is. Now, whether that's being pushed by consumers or by manufacturers, and you know the typical manufacturers we're speaking about, that's for the market research folks to determine. Okay, so I talked about integrated cockpit controllers. There's another segment of the industry which is growing, and that's autonomous driving and driver awareness functionality. Visteon's involved in that as well. We have on the left some collaborations recently we've done. In the center, we've got customer partnerships, and on the right-hand side, I'll just call it consortiums that we're involved in. So Visteon's involved in autonomous driving and driving awareness as well. Okay, so size, just to give you an idea of kind of the world I live in. We're not a small company, roughly north of $3 billion in sales annually, roughly 10,000 employees spread over 18 countries. We're headquartered in Van Buren Township, Michigan, which is where I work. That's an area 10 miles west of Detroit by freeway. Manufacturing footprint. So yes, obviously we have to, as a tier 1 supplier, we provide complete solutions to the automotive manufacturers, meaning the entire instrument panel or an entire radio or the like. So this gives a footprint. We have about 1 million products per week that we run out of 19 different locations. engineering footprint, what's significant here that I like to point out is, okay, I'm in that little orange dot over on the upper left, about 50%, roughly north of that, of our engineering is in software, and we produce somewhere around 134,000 lines of code a week was the latest metric. So again, we're not a small team. Okay, a little bit about automotive software. This is where it gets a little sticky because it depends on what part of the automobile you're talking about here. If you look on the left, today there's approximately 30 to 100 controllers in a vehicle, depending on the vehicle. And the trend is to consolidate that into a handful. And why is that? Well, if you heard the keynote from yesterday, what are your beads of worry on the left versus on the right? If you're a manufacturer and you want to decompose a feature to 30 to 100 suppliers, all trying to achieve one goal, is it easier to do through 100 different architectures and companies and teams, or 5? So that's kind of the trend. The orange on the right shows where Visteon's going to kind of live in the cockpit and the driver awareness world. Okay, this is another view of kind of the same story. Cockpit, domain controllers, autonomous driving, kind of separate, but trying to take all of the, or many of the functionalities that I described in those 30 to 100 controllers and paring it down to 2 or 3 years. Okay, so again, what are the things that worry most software architects within the automotive industry? Security. And when I say security, I'm not talking about someone smashing the window of the car and stealing it. Okay, at one time that was a concern. We're talking cybersecurity here. And why is that a concern? Most of those controllers I was speaking about earlier possess multiple networks. And those networks have the same vulnerabilities potentially that you'd be familiar with. So a lot of those controllers are on Ethernet. Some of them are on cellular. So we have many cybersecurity concerns. Functional safety. This is a transportation industry concern for the most part. We have rigid standards from ISO and other organizations that we have to meet depending on where we're putting these products in the world regarding functional safety. So this dictates not just how you develop the code, but how the code functions. And there are rigid tests for both of those. The next is over-the-air reprogramming. Again, that's related a little bit to security, but the concerns there are a little different in that not every MCU or SoC is on a network that's accessible. So we have to move the information from the network-capable SoCs to ones that are not. Graphics. I say 3D here, but graphics in general. Animations are much more complicated today. The displays are much richer than they were just a few short years ago. Current concerns. Why do I mention this? Nobody wants to go out to their vehicle in the morning and have to jump the battery. At the same time, nobody wants to get into the vehicle and have all of their memory wiped out. So we have some conflicting concerns when it comes to power consumption. Networking, big deal for us in that it's growing. A few short years ago, Ethernet was not in the vehicle. Cellular was not in the vehicle. They're there now. Bluetooth. And then the last 3 are driver awareness, driver monitoring, and analytics for everything we're talking about here. Okay, so what does that mean? It means there's a lot of code in there. All right, so, this is a rather old perspective, but 100 million lines of code per vehicle. I think we're well north of that now. Okay, so legacy software architecture review, which was the point of this talk, is what is this legacy software architecture? Okay, so we're talking about the driver information or information instrument cluster area. Left is and right are the same vehicle separated by a few years, a couple of years actually. And you can see the difference. On the left, we've got analog motor controlled gauges. We've got a small little LCD display. On the right, you've got a fully digital display. The odometer, everything digitized. This is the same vehicle from the same customer separated by a couple of years. So the question is, can the same software architecture achieve both of these? That's the challenge in the industry. Okay, so I'm going to go through just a few slides here on the views of the architecture we're talking about. Here's one. Now, these are not changed. These are views from, let's say, 1990. Okay. So what architectural pattern is this? I'm going to state it doesn't matter. Yeah, that's not really the point. But this was the way the architecture was laid out in 1990. The idea is a centralized server to handle the business logic, if you want to say, and then some servers or services for inputs and for outputs, applications on top. Another view, I didn't ask this at the beginning, but if you worked in the industry in the 80s and 90s, structured design was a thing, right? Before UML, we had Jordan and other ways to do this. This is a view of a Jordan diagram. You can look it up. It's good forensics to do when you get home. Another view of how data flows through this. So simple. Inputs can come from a network or a piece of hardware, flow through some sort of server into a feature and out the other side. So the way the software is built is around this reusability. And why is that important in the auto industry? Because I work at a supplier. We provide to a lot of the nameplates that you're aware of. They all have instrument clusters. They all have speedometers. They look different. They react different. But at the heart, they are a speedometer. They are an odometer. They are a tachometer. They are a gear indicator. There are warnings. There are telltales. It makes a sound. So we realized very quickly the idea should be to make as much of that reusable and configurable so that if an OEM wants something different, okay, we modify it. If we need different hardware, we can modify it. But there's got to be something that can be reused. So that was the basis of most of the architecture, was around this concept of reuse. How do you put an application together then? Well, a team responsible for that particular product would take the middleware, let's call it, or infrastructure, reuse it as is, assuming that we have the components already. They would configure some of the components for the hardware specificity, configure a few for the specific requirements from the nameplate, and then write maybe some very specific application components on top of it. And we did that time and time again for decades. As an example of the success, even at the hardware level, one single software architecture without modification ran on this. This is a small subset on these MCUs. And if you just look at what MCUs these are, you can already tell the dates. Yeah? There's an AC11 down there at the bottom. Okay. So what were the guiding principles? Why was it done this way? And secondly, why am I discussing this? Well, it's important to know where you're coming from if you're going to make a suggestion on where to go. Yeah? It's very hard to navigate Google Maps if they don't know where you're at. Yeah? So the principles that the team was successful 30 years ago at, and still today, the design was simple and therefore effective. Teams could understand it. It was mature. The usability, which I listed on the bottom, was extensive. The documentation was very thorough. A very simple way to schedule tasks so that people could add things if they needed to. And the idea was around this, I call it pseudo client server paradigm. It's not in the traditional client server that we would know, but there was this idea of services and somebody needs access to those services. Okay, so the task was this. We have this architecture. We have these new products. Can this architecture, which we've used and proven and our customers love, be used for our new products? That was my task. My initial answer, without doing any evaluation, was no. That's a hard thing to sell. You have to prove it. And so this was the way that I tried to prove it. I used two things, entropy and debt. Okay, for me, entropy seemed the most likely thread I could pull on to try and convince the stakeholders that we needed to change something. And then I did a little bit of analysis with the debt, which we'll get into here in a second. So you can choose any definitions you want. When we started out, I wanted to do a little education of the team, the stakeholders who weren't familiar with these topics, on what I was talking about with entropy and debt. I chose these definitions. There's many out there. I would say choose the one that best suits the understanding you have with the stakeholders. Okay, so once I decided entropy and debt would be the tools, the question was, what were the metrics going to be? So given my knowledge of the architecture, I thought that for entropy, I could prove, or at least be objective about the results if I utilized file-based metrics, interface-based impact, and then CM or configuration management-based impact. Why did I choose these? I mentioned functional safety earlier. One of the big pieces of functional safety is traceability, bidirectional traceability, which means you must be able to trace a requirement from the customer through the system architecture, system requirements, software architecture, software requirements, implementation, test procedures, test results, and deployment and backup, both ways. And someone can come in at any time, pick a random requirement, and require you to do that. Okay, so even years ago we realized maybe the best way to ease our burden in decomposing the system is to say, all right, each of these servers, which I mentioned earlier, let's make those a separate file. And this is mostly C, written in C. And then we could trace a file to a designed component to a set of requirements. So based off that knowledge, I said, I think a file-based impact will tell me how many components are affected by any particular change we're trying to do. Interfaces, kind of the same concept, right? If the number of interfaces impacted is large, then maybe we're pulling on the right thread when it comes to chaos and entropy. And finally, configuration management. Why is that? I'll get into that one when I show you the results. When it came to debt, and here I specifically say debt and not technical debt, I like to use generically the term debt because there's organizational debt and process debt. And okay, it's going to be technical debt here, but I try to steer away from just saying technical debt. But the metrics I chose here were compatibility of the stakeholder requirements to what we could achieve right now with the architecture. What it would take to modify our designs, implementations, to meet those if it wasn't already met. And then prioritizing the stakeholders' requirements. And then somehow combining all of that to come up with let's say, a metric, a number, one magnitude that we could then compare. Okay. The next step before I actually did the analysis was to say, what kind of entropy do I want to look for? To try and simplify the work. So I categorized it three ways. Architectural entropy, infrastructure/middleware design entropy, and then entropy at the application level. When it came to the architecture, I tried to pick two of the larger worry beads to determine if that could prove or disprove my thought that entropy existed. And as I mentioned earlier, for instrument clusters in a vehicle, graphics support was becoming a larger and larger component of what we had to do. If you can recall, 15 years ago, no display, now a fully functional, three-dimensional with sophisticated animation. So to achieve that, we had to introduce graphics frameworks, either our own or third party. We had to introduce graphics engines. And so what was the impact of doing all that? Well, it added 1,900 files to our build. Now, that's just a number, right? I can tell you that's a majority of the files in the entire product. So more than 50% of the files were affected by the addition of graphics support, which meant potentially, if a customer came to us and wanted to change in graphics, we might have to change up to 50% of the software. So immediately that tells me the addition of graphics support did not mesh well with the architecture as defined. So we've got entropy there. Also interfaces, a huge number of interfaces were affected. Again, very difficult now to trace what interfaces need to be changed. Second worry bead is regarding network. For instrument clusters, network functionality, I mentioned Ethernet new, high-speed networks new. So again, we looked at the file impact and interface impact there, very large as well. And we moved on to infrastructure. This was more of a design, not critiquing the architecture, but the way to design new functionality within the infrastructure to meet what was expected. And when it came to the design, just adding some new memory management technologies to an existing memory manager affected, again, a huge number of files and a huge number of interfaces. And then finally, CM package entropy. Okay, configuration management. The way it was done is that we create these reusable packages that can be deployed onto products. So they have a generic name. Let's talk about the odometer. The thought is all odometers are the same. They may look different, but they all are the same. So we have an odometer package. So I wanted to go through the entire list of all the packages that we're using from the configuration management system and say, okay, how many of these are truly being used, how many are being reused, and how many are not effective in what they are used for. And you can see totally, what is that, 35%, so a little over a third of everything in our CM repository was either not used or used only once here and changed and used differently over there. So that proved again to us that we had some entropy, some growth in what we thought was reusable. It's not even reusable anymore. Finally, at the application level, we talked about that idea of a feature server, input server, output server. So these applications should be developed based off feature servers. When I examined just a small subset of the applications, I could find that less than 5% were even adhering to the design paradigm that we had described. So the architecture wasn't being used as we wanted to be. When I asked why that was, they were saying it could no longer, the developer said it could no longer meet the needs. Okay, so let's get into technical debt. This won't take too long, but these are not, let's say, real. Okay, I had to generalize this for the presentation. The idea was we took a set of stakeholder requirements. It was a rather large list. This is a small subset. Then we allowed the stakeholders to give us priority, low, medium, high. We tried different things. That's what worked best. Okay. Next, we analyzed, could this be met with the architecture as is? The rating here was 1 was mostly, 2 was partially, 3 was not at all. And then effort to meet completely. So if we had to modify it, what was the effort? 1 is small, 2 was medium, 3 was a lot of effort. Okay. And we came up with a technical debt factor, which is a number. This is nothing more than an addition of low being 1 plus 2 is 4. Okay. What did that mean? Okay, for us it was very simple at this point. Things with a large number, a lot of debt. Things with a low number, not much debt. And this was not mandatory, and it's not mandatory for you, but it's a suggestion. You can classify your debt as well. There's an SEI paper out there on how to do it. The paper's for a different topic, but I found it useful here. You can actually analyze your debt and convince yourself that not all of it is actually technical debt. Some of them are improvement actions that don't have any side effect, so shouldn't be treated as debt. We reduced a few of the items based off that analysis. Okay, so where did we end up? Again, we categorized the debt in 3 ways. architecture debt, infrastructure debt, and application debt. And the idea was, based off those stakeholder requirements, we took each one of them and decided, where is the root cause of this? Is it from architecture? Is it from our infrastructure, those reusable middleware pieces, or is it at the application level? And so each stakeholder requirement, we started with the 9s and worked our way through and categorized them. And what did we come up with? We came up with 3 teams to attack both the entropy and the debt. The architecture team now had a list of entropy and technical debt prioritized items. The infrastructure team had the same, as did the application team. So what did we do with that information? What we concluded, and we were able to convince the stakeholders, which is really our job here, right? I mean, we always want to redo everything. But the point here was this was going to be a big investment. So you have to convince the stakeholders based off real data that something needs to change. And that's what we were able to do. Our choice was this: evolve the existing architecture, which had been done for years, or introduce a new architecture. So we were able to convince them a new architecture would be required. Okay, summary. Point 1, analysis of legacy systems, or any systems, any subsystems, any component, any whatever. You need to use a systematic approach. It doesn't have to be this approach. This is just an experience report of what we had done. Back up your conclusions with data, but you should collect the data before you make the conclusion. All right? Don't have opinions. Secondly, not all debt and entropy is the same. What do I mean by that? Well, architecture debt is not the same as application debt, is not the same as organizational debt, is not the same as process debt. And don't look at it all the same. That's kind of the lesson learned there. Helpful thought that I had to keep reminding the team is entropy is often the side effect of technical debt. Okay? And what does that mean? Well, okay, debt is a choice, yeah? Sometimes. And it's also a choice when to attack the debt, when to reduce the debt. But you have to keep in mind that those choices of when and how to do it can lead to entropy. So you must keep an eye on that. And finally, we need to strive to answer the question why the debt and or the entropy exists before we resolve it. The team I was working with, we're constantly, this is our nature, right? How are we going to fix it? How are we going to fix it? That's true. It's very important. I like to keep reminding them it's just as important to understand how did we get here? Well, why are we here? You need to understand, and we gained a new appreciation for the architecture that we had been using for years by just asking why is it this way?